Our next speaker is George Shakan from Oxford, who speaks on a large gap in a dilate of a set. Please.
Yeah, thank you. Thanks for the invitation to speak here. It's a pleasure. Yeah, so let's get started. So this is on a actually just a paper of mine that's somewhat recent. It's a short paper. It's only a few pages, but I wanted to talk about it today. But yeah, it makes it a good topic for such a not a full hour talk. So okay, it's not too different than maybe some other talks. So let P be a prime, and let A be a subset of FP. So this is our general setting. So now we want to define the largest gap in A. So, okay, you might already kind of know what that means, but I'll define it. So let G of A be the largest gap. In A, so let's just formally define it, i.e. the largest integer G of A, so that there's a translate of a interval that's disjoint from A. So satisfying. Right, but this might be what you expect the longest gap of a set to be. So there's a large interval that is disjoint from A. Okay, so this is a definition by Pigeonhole. I have written that G of A is at least, P over A minus 1. And this bound is tight by just taking your points to be kind of equally spaced. Right, so you have this this lower bound that's tight, so there's nothing really interesting more to say in this situation. But now we're gonna kind of we're gonna dilate our set by some dilates, and then see if some dilate has a large gap. So that's the general question. So let's write that out. Okay, so this is just a standard definition of a dilation of a set. So the general question or the motivation for what I'm going to talk about, which as far as I know is due to Green, to Ben Green. It's okay. Such that, okay, let me change that. That's a little messy. Okay, so sometimes the answer is no, in particular when like the size of A is quite small or quite large. Well, I guess quite large is really the case you have to be concerned about. When you're quite small, actually, you're good to go, but we'll talk about that. But yeah, so when can you assert this is the case? So for which sets A, hopefully something that just depends on the size of A, perhaps that would be nice, or maybe it's just true most of the time. Okay, here, I mean, just by the pigeonhole argument, we get that P over the size of A is basically a lower bound for the largest gap. So you're asking, can you significantly improve upon this trivial lower bound? And by significantly improve, I mean by a multiplicative constant. So this is the general question. I'll talk a bit about some motivation perhaps a little bit later. I mean, not too much later, obviously, but a little bit later. Well, let's just talk about some general facts. So General facts. So 1, it's true for any C. Okay. I guess I only have one fact, but I think of it as 2. Okay, so true for any C. If the size of A is really small, that's a nice exercise. It uses Dirichlet's, or one proof uses Dirichlet's theorem about approximating rationals. Or if, or approximating by rationals, or if A is, proportional to the size of P. This one's a bit harder. It uses Semroni's theorem. Yeah. Okay. So it's true at the kind of extreme points. So when the size of A is small and the size of A is large. Okay, so a case of interest, at least to me, is if A is P to the delta, where delta is, and if you don't even want to think that generally, just think delta is 1/2. It's perhaps the most interesting case. And in fact, the reason why this is an interesting case actually goes back to Sidon sets, which was the topic of the previous talk. So we'll talk about that a bit at the end. But yeah, so you have a subset of FP. It has P, size P to the delta. What can you say about a large gap and some dilate? This is the general question. I wish I could prove for any C, but I cannot. But one thing able to prove is okay. So you should basically ignore this term. It's small, say, if the size of A is small. So let's ignore that for a bit, but something like that has to be present. So basically, you can double the pigeonhole bound. This is the content of the theorem. So if you're allowed to dilate your set, you can choose a suitable dilate such that there's a gap twice the size of what you get from pigeonhole. This is the rough, or this is the what's going on. Okay, so in general, it would be nice to. We have a question. Improvised talk. Okay, so this was planned. Don't worry. So the ansatz of this, I mean the ansatz of the proof. So the starting point. I mean, okay, the proof is only about a page or a page and a half, so it's not so long. But we can't give it all here. So 1 up to m. So b is like your interval. M is like basically g of a or something very close to it. And you suppose it's not, so it's probably the g of a minus 1. So you suppose that every translate of this interval intersects every dilate. So this is for all d and fp star and for all t and fp. So this is what happens if you do not have a large gap. So i.e. no large gap. So what you would like to conclude is that from here you would like to conclude that the size of a you would like to make some conclusion on m in the end in relation to the size of a. Okay, so Okay, so the next step, which may look very familiar or extremely foreign, depending on your experience. Okay, so you define this polynomial. It's a polynomial in D and T. I guess it has degree the size of A times the size of B plus 1. And the point is, by our assumption, W of dt vanishes on fp squared. So this is actually just it's an equivalent, you can check that it's actually equivalent to the original hypothesis. Okay, so you have this polynomial that vanishes on fp squared. I mean, so you can apply the so-called combinatorial Nostellensatz of a ln. Oops. Which gives, you know, something like W, well, okay, it gives this. U of dt plus.
George, can you move the slide up a bit? Yeah.
Did I? I see. Like this. But yeah, I had scrolled anyway. But yeah, I see what you're saying. Okay, I'm not gonna fully write out what this gives, but it gives something like you get some decomposition of your polynomial, then there's some degree assumptions on U and B that you can make. This is the starting point. There's still some work to be done from here. It's a, you know, you can try to figure it out if you want, but this is the starting point of at least the proof I gave. Right, so yeah, you apply the polynomial method, and then you still need some tricks, but eventually you'll end up getting that this interval has to be large. So some steps, some additional steps, ideas. I see another question. Yeah, I can comment 1 sec. And then you get, you know, m is greater than or equal to 2. So I guess it was asked in the comments. Yeah, what's the? Yeah, okay. I proved this theorem. Is this the best you can do, or can one do better? The answer is I don't know. It's an interesting question. I think. I mean, this is the general question. How large can you take C? In particular, when the size of A is p to the 1/2, say, can you take C to be larger than 2 would be the first question. And can you take it arbitrarily large would be kind of the general question that one could ask. Yeah, I don't know if one can do better than 2. Yeah, would be nice to know. Okay, so what was the motivation? So I should mention. What time should I stop, Mel?
10 minutes more.
Okay. So the motivation. Okay, so A suitable variant, which I'm not going to talk too much about here, but what a suitable variant would actually mean, it's not so obvious, but would an improved bound for the lower bound for Ceton sets. So I guess I should mention that it's a lower bound. And I think this was Ben's original motivation for asking. So improve lower bound for the size of a Ceton subset of 1 up to n. Right, so we know, it was mentioned in the previous talk, well, we know that let's call this A, say A. So we know we can find an A so that this is true. Okay, something, I can't remember the exact constant here, but some fixed constant anyways. So something like this is true. But one question one could ask is, can you add this C here? So can you get arbitrarily far from this n to the 1/2? So something like this. So what's known is like C is some fixed constant, like 3/2 or something like this. And the question is, can you improve by an arbitrarily large constant? And this is a nice idea. The point is you take a Ceton set. Well, okay, so there's kind of a couple. So what's going on here? So some lower bound Ceton set constructions are actually Ceton sets mod n for some n. So not only are they Ceton sets in the integers, they're actually Ceton sets mod n. And so the hope would be to suitably dilate your set mod n. Okay, mod n. So that there's a large gap okay at the end, or like near at the largest portion, say near n. And then if you could achieve this, then you could actually prove that you have a Ceton subset of something that's just as large. The Ceton set would be just as large, but it would actually be contained in 1 up to something smaller than n. So this is the point. So why did I say you need some suitable variant? Well, first of all, yeah, the question we were talking about was for a prime, but this n isn't known to be, the n that you get from these Ceton set constructions isn't known to be prime for infinitely many primes. Yeah, that would rely on some number theory conjectures that are quite hard. So anyways, I have a couple more minutes, so I should to end. So I'll highlight one simple case. it's the case, I guess so, and that is when A is equal to H, which is I use H because it's a subgroup of FP star. So a multiplicative subgroup. Good. So yeah, if you have a multiplicative subgroup, dilation, we understand a bit better what dilation is doing. Of course, we don't necessarily understand the additive properties as well. So for instance, can we find a large gap in H itself, which is a bit stronger than the, but in H. So this might be related to some questions people have thought about, especially when H is large or something. So you could think of this as a nice starting point. Yeah, to think about the question. Yeah. Okay. I think we'll stop here.
All right. Thank you, George, very much. I see a question. Actually, Oliver, you can ask it directly, I believe.
Are there any constructions for this problem? I have a vague memory of some fairly easy probabilistic constructions. Yeah, so the probabilistic construction should give something like C is equal to log P. Yeah. I think that's probably what you were asking.
Hi, maybe, can you hear me? Sorry.
I can hear you, yeah, loud and clear.
Yeah, yeah, I thought that there was a construction of a set which had this, I can't remember the notation, but for all dilates, oh, I haven't thought about this well enough, sorry. So you can show that so the trivial band is P over A, right? And I thought that there was a construction where this quantity was less than like P over A squared or something. I think I thought about this problem like 4 years ago and I've forgotten about it. So I was hoping you could refresh me.
Yeah, as far as, yeah, so I think constructions like this of this flavor would give something like C is equal to log P. For this question.
Do you think that the best that you could possibly hope for is about C being about log P?
Yeah, exactly. You have to, maybe it's like log P over log A or something, or sorry, log P over A, but like, yeah, something like this.
Okay, thanks.
Wait, sorry. Yeah, something like log P, but you have to be careful with the size of A. Yeah, you have, I think you have.
Is that just taking a, sorry, is that just taking a P random, oh, sorry, I should say a Q random set?
Yeah, exactly, yeah. Yeah, I think yeah, you might have a somewhat relevant paper with Ilya and others on some questions that are somewhat of a similar flavor.
Okay, thanks for the answer.
Yeah.
Other questions for George? If not, thank the speaker, and we start again in 5 minutes.
Yeah, thank you. Appreciate it.